So, as she said, this is going to be a little bit different from the usual algorithmic game theory. So, there will be games, there will be algorithms, okay, but it's usually not in the mainstream algorithmic game theory. Okay. So, the goal of today is to understand this model called parity games. Okay. Has anyone seen this before? No. Okay, that's good news. Okay. So, these games are somehow a fundamental tool in the study of logic, automata theory and verification. So, I am not going to say why, okay. You just need to take my word that this is a fundamental tool. Okay. I can point you out to some nice tutorials where they show the how parity games are useful and so on. Okay. So, this is the next question. So, why are parity games interesting to the algorithms community? Why am I kind of reaching out to this audience? Okay. So, the biggest interest in parity games is in the fact that no polynomial time algorithm is known for solving parity games. Okay. We will see. So, it is known to be in NP intersection co-NP, okay, and very recently, okay, in 2017. So, actually it's a little bit of, so I started giving this course called Games on Graphs. I should admit I work on automata, verification and stuff. I never worked on algorithms and so on. I just started reading this subject in 2017 just because some of the students were they wanted something new and so on. And at that time the best known algorithms were exponential time. Okay. So, but parity games are known for like several years. I mean at least mid 90s, I am pretty sure, like maybe even early 90s and so. So, like more than 30 years it is known, and yet the best known algorithms were exponential time. And then in 2017 suddenly there was a big breakthrough, like a quasi polynomial time algorithm came into. I will tell you what it means if you are not aware of what quasi polynomial is. Okay. And then somewhat surprisingly, after people knew that it is possible, there were like 4 or 5 papers immediately, like in succession, different quasi polynomial time algorithms, all of a different flavor. So, to the extent that right now I can't even keep track of the algorithms that are known to be quasi polynomial anymore. So, there are several of them. Okay. So, here is probably the gentle plan for today. Let us see how it goes, and based on that we will adapt. Okay. So, the idea in lecture 1 is to just kind of get ourselves familiar with the model, like because if you are not aware of this, it needs some time to understand what this is, and we will also see some algorithms for some of the simpler cases. Okay, that is planned for lecture 1, and in lecture 2 we will see some classic algorithms which run in exponential time. Okay. Now, in lecture 3, if we reach up to that point, we will try to kind of look at a quasi polynomial time algorithm. Okay. So, there is a very good exposition. I will talk about it. Okay. So, this is the plan for today. So, your takeaway should be one model, 2 algorithms and possibly an idea, okay, in the final thing. So, that is the expectation. Okay. So, let us go to this first model. So, let me start with the formalism. So, this is a game on a graph. Okay. So, what are you given? I mean, what are the what is the game and so on. So, assume that there is a graph. Okay. Now, this graph is a little bit different because the vertices, some of the vertices are circles, some of the vertices are squares, right. So, there are 2 players, player 0 and player 1, okay, and they are given this graph. So, player 0 controls the circle vertices and player 1 controls the square vertices. Okay. how does the game proceed, what are the rules of the game, what is going on and so on. So, initially no, I did not call you. So, initially, sorry, this is Siri, he thought I, yeah, no. So, no, I did not call you. I do not know how to get rid of you. So, yeah, anyway. So, so there is an initial vertex, okay, and okay, and then the players, so you assume that there is a token which is kept on some vertex, okay. Now, if the token is on a 0 vertex, player 0 will choose where to move it, okay. Maybe player 0 chooses to move this way, let us say. Now, the token moves to some other vertex. Now, depending on who is controlling that vertex, that player will move the token, okay. It is a very simple game. There is a graph, there is a token, and depending on where in which vertex you are, the corresponding player moves, okay. So, we assume that the game continues forever, okay. So, it is like a mathematical game, so we can make these kind of assumptions. So, the play is an infinite word, okay. You see this is so this comes in very handy in automata theory and logic and so on to look at infinite words. So, if okay, anyway, so but the game is assumed to continue forever, okay, and this is a play. A play is a sequence of vertices, how the token moved, V0, V1, V2 and so on, okay, very good. What is the objective, okay, you are just moving aimlessly, but you need to have an objective, right. So, the winning objective is a set of plays, okay. So, for each player you say okay, they have to partition. So, for player 1 you say these set of infinite words are winning for player 1, okay. The others are winning for player 0, okay. So, we are going to play, if the result of this play belongs to the winning set of player 1 wins, otherwise player 0 wins, okay. But you see, like, I mean, how do you even give the set of infinite words? I mean, you have to describe it in some way, right. So, we need a way to describe these objectives in a finite manner, okay. So, we will see some objectives, parity will be one, but we will start with what is called the reachability objective, okay. So, you are given this game graph, okay, and you mark a bunch of vertices to be target vertices, okay. So, in this case 8, 9 and 10 have been marked as target. Assume you start from 0, okay. The goal of player 0 is to avoid going there, okay, and the goal of player 1 is to push the play towards 8, 9, 10, okay. Can you see how to play this game? Assume that you are here, okay. How should player 0 and player 1 play? So that I will also put the objectives here.
So, push means like move the tokens.
Move the tokens, yes, 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 correct, yeah, correct, exactly. So, how do you, how should player 1 or player 0 play so that their objectives are reached? Maybe one of them has no chance.
Because 0 goes to 1, then it goes in that loop itself. Yeah.
Very good, okay. So, if 0 does this, 1 can do this. So, it is a bad move for 0 to go here, okay. Oh, I am sorry, 0 has to avoid, okay, okay. Yes, and 1 has no choice. So, which means that 0 is winning for player 0, I mean the vertex 0 is winning for player 0. So, let me just mark it. Here player 0 wins, here also player 0 wins. If, what I mean is, if the game had started from here, okay, player 0 would still win, because there is no other choice, player 0 will cleverly do this. What about this?
One more thing, like player 0 can't move token on a square, right?
No, no, no. Yes, yes, I mean if the token is, no, no, I understand your question. So, if the token is here, it does not matter who controls the target vertices, he can move it anywhere, it does not matter whether it is controlled by player 1 or not, it only matters at the current vertex who moves it.
So, in this game the only target of 1 is to go till 8, 9, 10 and 0 is not to.
Not to go, that's all.
Nothing.
Not, yeah. What about 2? Let's see. Player 0 wins. Why? Can you say? Come again?
He'll push to 3
And then 3
Okay.
and then 3 as 3 controls.
Very good. Yes, that's all. So player, this is player 1's vertex. Player 1 can okay, yeah.
Go back
What
to
if a
3.
player, yes, it's not over. So if player 1 pushes it here, then player 0 wins. Okay.
Push it back to 1.
Yes, and win. So let me first mark this vertex as winning for player 0. Okay. What about this? If player 1 moves it here,
Now player 0 again can get it into a loop by pushing to 7.
exactly. Okay. So that is good. So 0, 0, 0, and so 0. I hope there are some 1s also. Let's see. So yes, there are.
No,
So
it
if
starts
there
at
are
8.
moves there.
Now it won't go to any other.
So
So
what
there are
if
no other
we start from here?
Then
Clearly player 1 wins because it is under player 1's control. Okay. 6 again, once again, you see. And these are already winning for player 1. So by default player 1 wins if you start from there. Okay. So you get a feeling of this reachability game. Good. So this set of vertices are called the winning region for player 1, and this set is a winning region for player 0. So you see, somehow you were doing this thought process and telling out which player wins from where. This needs to be made into an algorithm, right? So before we get into that, this idea of how should each player play, okay, let us formalize that. Okay. See, because you see, like you were telling us, how should each player play. So for instance, in this case, player 1 better do this and not this, right. So player 1's strategy is to do this. Okay. Similarly, well, let us say for 0, yes. See, let us look at this vertex. Okay. What should player 0 strategy be? It should not be this, because it player 0 will lose. So the strategy should be this. Okay. That is all. So you have understood the notion of strategies. Let us just put some formal symbols to that. Okay. So what is a strategy? See, of course you can give a very generic definition of a strategy. I look at the history of my play and then I say what to do next. So in general, a strategy for player 0 is a function which maps words that end at player 0's vertex to the next move. Okay, v0, v1, vi, and now suppose you are at v, what to do. Okay. But for our purposes and for today, it is enough to look at what are called memoryless strategies or positional strategies. You do not care about how you reach that vertex, you might have reached it in different paths, but you are always going to play the same move. Okay. They are called positional memoryless strategies. So they are very simple functions. For every vertex, you just of player 0, you just say where to go next. Okay.
Notation about the V star represents what exactly?
It's actually not important for today, but anyway, so like see what this says is that, see, in general a play can be a big word, right. So suppose I reached a vertex v, okay, through different histories.
The V star is the history.
Yes, v star is a word, that is all. Yeah.
V naught is what?
v0 is a set of vertices of player 0.
So the circular ones, right?
Yes, the circle. See, 0 circle. Okay. So
But like what we saw in the last game, it doesn't actually matter.
It doesn't matter, yeah, I know. So I gave this general definition, I do not know why, but there are games for which it matters. Okay, there are objectives where you really need to care about how you came to that part. In the simple games like reachability and so on, it will not matter.
Like we are reaching V0 and from there V0 we are going to some V, right?
Yes.
This arrow that we are showing.
Yes, yes. See, let me give you an example. Suppose the objective is I want to visit vertex V1 and vertex V2. That is my objective, let's say. Okay, a play is winning if both V1 and V2 are part. Okay, in the previous case it was V1 or V2 and it was okay. In this case, suppose I have to visit both, then you need a memory to know whether you have visited V1 or not. Okay, and based on that you will adapt your strategy.
Like I was thinking that we want to in this first line V star V0 and then going to V. So shouldn't it be V0 star because it would be history till reaching V0 or
I'll tell you why it is not. Okay, see, suppose this is a vertex 3. Okay, suppose I reach this by 0, 1, 0, 2, 3. This is not in V0.
so 3 is V0.
3 is V0, but this word 0, 1, 0, 2, 3, this is a word in V star where V is a set of all vertices.
So that was capital V and then there was a small V there.
Oh no, all of them are capital actually. Maybe it is written small, but no, everything is capital. Capital V, capital. Oh, this is capital V. The set of vertices from which player 0 plays.
Yes.
Honestly, it is not important. Okay, so the only thing that is important is this positional strategies, which is that.
Okay, can I ask a question?
Yes.
So you need the definition to be this because player 0 can only move a token when it is at 0th position.
Yes.
When it's a 0 vertex.
Yes.
So whatever the history it is, you have to be at V0 for player 0 to have any legitimate move.
Correct. Yes.
That's what this
That is what this
and
is.
similarly
Huh.
player 1 has to be at V1
Yes.
to make it a legitimate move.
Correct. See, I mean, essentially a strategy is how a player should play,
Play, exactly.
and a player plays only when
Yes, legal moves.
yes, a player plays only when they are at the correct, vertices, corresponding vertices. So that is the
So this memory, this thing.
Huh.
So as long as I can ever get to V0, there's a history. There's a string by which I can get to V0. I can pump it up as many, like all those are legitimate moves to get to V0, right? Because I can go around that circle bunch of times and again come back to V0. And if there was, if there is a short history
Okay.
via which from V0 I can get to my target,
yes.
then all longer.
Kind of, this is the argument to say that positional strategies are enough, as long as the objective doesn't really care about the pumping. You see, like.
Oh, the objective should be like, oh, I don't want too many long length paths. Like you reach quickly enough. So pumping, what actually does the pumping say? I wasted time going around.
Yeah, see, that's what. See, it's not evident because we are looking at reachability objectives.
Yes.
There it really doesn't matter. As long as you reach, it's okay, right? But there are objectives where you have to do two things. Let's say you have to visit V1 as well as V2, and then you need to remember whether you have visited V1 or not, and then based on that your strategy will change. Okay, so that is the point. So there are plenty of objectives. Like, I mean, we will not even go into that.
If a node is marked 1, that means like if I start at a node, the token starts at a node, 1 will win.
One will play.
No. I'm
Oh,
saying
okay, the winning region. Okay.
one will win. So I mark it as 1.
Huh.
The strategy for player 0 would be to not reach that.
Yes, exactly. Yes, that's the idea. Yes. Okay. Well, okay. So, assuming that what strategies are clear, what is a winning strategy? Okay. So, one of the players, let's say player 1, plays according to a strategy. Okay. So, that means at every vertex of player 1, there is a single outgoing edge that conforms to that strategy. Okay, you know that I am going to play this one only. It is winning if every play hits the objective, right, because even if one of the players does not hit the objective, it is not a winning strategy. There is a path where 0 will win. Okay. So, that is the meaning. So, there is this alternation here, a winning strategy, it is a winning if you have a way so that all of the plays that correspond to this are winning. Okay.
So can I have
Huh.
a path on which only 0 can move, and then that path can be in contact, like shortened into one edge, right? There is no point in having
No,
a long
no.
path where only the same player.
Yes, 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 yes. I see. It depends on whether that player has other moves. You see, like.
Okay. So suppose it's a long path where only 0 is moving, and there are these side edges coming
Yes.
out, where it can pass the token and then one starts swinging.
Yeah.
Okay, that is different from.
Yes. You see, I mean, I understand where you are trying to summarize the graph in some sense.
Yes.
See,
I want to get rid of redundant long paths.
yeah, but
But that's not possible.
I mean, it's not in general possible, I would imagine. Okay, but that's I mean, maybe there are places where you can do that. So, in the sense, because I feel like you go like this, in one place you want to do this, and in another place you want to do something else, and you have to effectively summarize. Like you have two ways of going,
Yes,
and you cannot.
preserve those possibilities.
Yes.
And somehow still reduce the graph.
Correct. So nice idea, but I mean, I've never thought about it. Like, okay, fine. Let us move on. Huh? Like, maybe let's just move on to this. Let's go directly into the algorithm for finding winning strategies. So we know what to do, but let me just formalize it into an algorithm. Okay. So, I give you a graph and I say that these are target vertices, these are winning for player 1, let us say, okay. And then I want to compute the winning regions of both the players. Essentially what we did in that example can be translated into an algorithm. Okay. So, let us start from T. Okay. All vertices in T are already winning for player 1. So, there is no decision to make, right. So, I will initially mark, oh by the way, this is the iteration number, it does not mean the player. Okay. At the 0th iteration, sorry, like there are so many zeros and ones, but I hope you understand the semantics of each 0 and 1. Like this is iteration 0, you just put all the T into player 1's region. Okay. Now, in the next iteration, you look at player 1's vertices where there is a way to move here. Okay. If that is the case, you mark this as player 1's. If I look at a player 0's vertex such that all of the edges get into this, that is also winning for player 1 because player 0 has no choice. Okay. So, I will put that also there. This gives my first iteration. Now, I take a union of them. I go to my second iteration, let us say like this. Now, in the second iteration, I have a figure here, that is okay. Yeah. If I have a player 1's vertex, which either, I mean, which goes here, okay, then I pick it. Okay. And if I have a player 0's vertex, which either goes here or here, does not matter, all of them are marked winning, then I pick it. Okay. I just keep doing this, that gives me an algorithm from the back.
Sorry, what are the vertices in iteration 1? So, like what vertices are you considering?
In this iteration,
Yeah.
I am just going across every vertex just to be, okay, I look at a vertex and I see if it has an edge into the currently winning set. Depending on whether it is player 1 or player 0, I need to make an exists here and a for all here. Okay. That is the only.
But a player 0 can come to that square, right?
Yes, then also player 1.
Yes, token comes to that square.
But
Player 0 does not come to
player
that.
0 tells the token to come to
Yes.
this. So here we are saying this square has one edge to the T, and it may have different edges also.
Yes,
Right.
but player 1 has control there and player 1 will want to win. So, player 1 will move the token there.
But it could also happen that player 1, so I wanted to say that
Huh.
player 1 made the token to come to that square. And now player 0 will play from that square.
No, that is not possible, right? Because from a square, always player 1 will play.
Okay.
Okay, and from a circle, always player 0 will play. We need that. Yeah. So that is, sorry?
Also, we have to ensure that the player 0 vertices who are going to this T set of vertices is not going to some other vertex which is a winning situation for 0, right?
All of them are.
That's why all.
That's why, yes, there are no other edges. Correct, yeah. All of them should be going to the currently winning fixed thing. Yeah. It's actually a graph reachability extended with a there exists for all. You see? That's all. Okay.
But do there have to be vertices that are like marked in the first iteration?
Oh, all the T vertices will anyway be marked, right? Because they are in the 0.
Right, no, but in the
Right. Suppose at some point this has to stop because the graph is finite and at each iteration you're picking one extra vertex, and at some point suppose you don't pick anything, so you reach a fixed point. Okay, what happens then? So this is the good question. So this is the thing. Okay, so assume that you have done some I iterations, in your case I is 1 or whatever, and then you don't have anything else to do. This means that in the rest of the vertices, player 1 has no way to go inside. Player 1 is stuck here, and player 0 has a way to trap player 1 here. It is not a for all going this way. So there exists a way in which player 0 can stay here. Okay, so and this is a trap for player 1. Player 1 has no choice but to stay here. Player 0 has a strategy to keep the player 1 here. So it is a winning region for player 0.
But in the example that we saw, I saw that there were two circles that were connected to each other. It can't happen, right? Or can it?
Wait. Let us just. This is the example, right? See what will. I mean, I'll just quickly run through because it might. See, in my first iteration, I will pick this one, this one, and this one.
So you start from 0. Then.
No. We don't start from 0. We start from the back, from the set of reachable. Set of target vertices. So that's what I'm saying. So I will put this, maybe I'll give the number at which.
Like I had doubt in the fundamentals of the game where we were saying that
Okay.
the 0 can play from circle itself
okay.
and 1 can play from square. So after say like from 4 if 0 puts to the 6 then player 1 can't even play, right? If we start from 4 and 0 pushes it to 6.
That's okay.
But player 1 can't play there. So
that's the structure of the graph.
Edge exists. Like it is not valid, right?
No.
According to the rules.
So
But player 0 has to like move to the 9 or 10 only, so it's a winning move for player 1.
it's not alternative.
yes, it's not alternating. Yeah, that is the sorry. Yes, it doesn't have to alternate. Players, yeah, maybe that was the confusion.
Yeah.
Oh dear.
Yeah, that's why I
Okay.
was asking you can have a long path where the same player is
Oh,
playing
I
and so on.
see. Okay.
But this is a clearly winning strategy, right? Because 0 can't move away from having to reach 1.
Yes, correct. So that's what will happen.
That's why 1 is a winning strategy.
No, in fact, let's do the iteration. See, at iteration 0, 8, 9 and 10 will go inside. Okay? And in iteration 1, this will go inside. Okay? Now, no, 6 will not go in 1. 6 will go in 2.
Yeah, it will go to 5.
6 will go in 2.
All its edges are going.
Okay? And then, so 4 will go, no, that's all, nothing. 2 iterations it will stop. Because you see, none of the other vertices, see this one has an edge outside. This one also has an edge outside. So this will be like a fixed point. It will be a winning region for player 1.
And squares don't have any edge to go in.
Yes. And so we claim that this is the winning region for player 0 and this is the winning region for player 1. Is that okay?
Player 1 can't play from a circle, right?
Correct.
But
See, when we say it is winning, a player 1 can win from a vertex which belongs to player 0. This is possible because we are looking at plays that start from that vertex. You see, player 1 can win from here because whether player 1 wins or not, it depends on the play. not the vertex that is controlled. You see, like
The player 1 can't play from circles. Right?
yes, player 1 cannot play, but player 0 will play. But what can player 0 do?
But I am saying so. If player 0 starts at 4 and it pushes to 6,
Uh-huh.
like it can't push to 6. So like one can't.
It does
play
not
from-
want to push to 6. That's the thing.
But even if it pushes to 6, one can't play from there.
Yes, one can't. I agree.
So nothing
No,
will
no. But
happen.
who plays from there?
9, 10. Yeah.
So player 0 again has to play from there.
Yes, because the token is there, player 0 has to play. Yeah, the game continues. Yes. Anyway, okay, good. So, can you tell the running time of this algorithm?
Maximum is
Yeah. N plus m, let's say. Oops. What is the running time? So, it is like every edge is visited only once. Okay, you don't have to visit any. Okay. So, we make an assumption, okay, by the way, that there are no dead ends. From every vertex there is an edge.
Unless it's a target vertex.
Yeah, but you know, just for
Then you can have the loops.
you can have the loops. We will see now where you may not have. Yeah, I'll come to that. Okay. So, and therefore, if n is the number of vertices, m is the number of edges, this kind of backward algorithm runs in OM, you can show. I mean that n plus m will just become OM, because m is anyway bigger than n. Okay? Good. So, let us move on to the next objective. Now we are going to make the game a little bit more complicated. First was reachability, now let us make it slightly more complicated. We are going to call it repeated reachability. So, remember our plays are infinite words. I mean, like you start from a vertex and it is going on till forever. So, here we will actually use the infinity assumption in the sense. So, a play will be winning if some vertex from the target set repeats infinitely often. Okay? In the sense the play has to visit T infinitely often. You can go out of T, but then you have to come back to T. Go out of T, come back to T infinitely often. Okay? Somehow I do not know, I mean they look like very weird objectives, but they are actually helpful in logic and automata theory. Now the question is, how helpful are logic and automata theory? That I am not giving an answer. Okay? So,
Previous setting, if one of the target vertices are reached, the game ends because player 1
yes, yes,
But
yes.
here it won't.
Here it won't, yes, correct.
But even in that game, there was self
But
loop
there's
on the
a
target.
self-
Yeah, I just put self loops so that assuming that because play is infinite, yeah, but the prefix will determine whether it is winning or not.
So how, given that this is an infinite number of times, how would you specify a winning strategy?
Once again, the strategies will be positional. You will see, like from a vertex, I will say what to do.
But like the fact that you are able to, like I shouldn't be able to quantify how many times T has been reached because the
Yes.
whole edge becomes finite.
Yes.
So I'm saying, how do I express this game?
No. I mean, it's a valid thought. So somehow you will reduce it to an easier question. You will see it become the number of times will never come into the picture. Okay.
So can we say that if we find a closed loop such that there are even number of circles and even number of squares, and there's a circle that leads to that loop, player 1 will always lose?
No. Wait. In this, you're talking about this objective, right? Oh, the previous one.
This is the first graph it showed. No, can we come to the strategy of those sorts?
Okay.
So can you speak again? What did you say?
This
So
one.
there are even number of circles and even number of squares that lead to a loop, and there's a circle that leads to a loop. There's no point that you can't force 0 to leave the loop.
Yeah, you can, as long as the zero vertex has a loop, you have a winning strategy. for
Yes, exactly. Yeah.
zero. You don't need anything else.
See, the structure of the graph could be very different. You see, it depends actually on the way the edges are. The number of vertices and all do not play a role. You see? Wait. So let us maybe let's start with this example. Like, see, just for, I do not know, I mean, for simplicity, I would say I made all the vertices belong to player 1, although there is a player 0. Okay? Like, in some sense, the question is whether player 1 can win or not, right? See, for instance, here, okay, player 1 can do this, and once player 1 is here, it's not helpful for him to just stay in this loop. It should go like this. Okay? So, this is winning for the Bucci objective, the repeated reachability. Now, what about this? See, although this is winning for reachability because you are there, once you get out, you cannot get in back there. Okay? So, this is losing for player 1. So, this is winning for player 0. So, this one and this one are winning for player 0, whereas this one and this one are winning for player 1 just simply by playing this. 0 doesn't even have to play. It will win. Yeah, you see, it's yes. It's a conceptual thought. You see, like assuming that if you play this, when you look at this graph, okay, and you see that if you fix the strategies of player 1, if the game proceeds forever, every loop in that graph will have an accepting node, right? Just by looking at the graph, you can imagine that. See, anyway, I mean, we cannot wait. You see, these are infinite words, so it's not a real physical real thing. It's just a conceptual model. Okay. Yes. This one, See, that was for the reachability objective, right? Now we have changed the objective. So yes. So I am saying, like, we started with reachability, then we will complicate the objective a little bit, then we will complicate the objective a little bit more. Okay. So, well, I have drawn this graph. Now, can you help me figure out what are the winning regions for player 0 and 1 for this repeated reachability objective?
First one is player 0.
Wait, I mean, take your time. Let me give names to the vertices maybe.
Do they have to be infinite number of targets, or does it have to be the same target? In the word
they can no, I understand what you mean. The target can be any vertex as long as in T, as is in T.
Doesn't have to be the same.
It doesn't have to be the same, but you see, since there are only finitely many vertices, if you see something from T occurring infinitely often, there will at least be one vertex which occurs infinitely often.
Yeah, inclusive.
Okay. So, what did you guys say? It was clear that this one clearly player 0 wins. Okay. Oh yes. No, so far nothing interesting. These also 0. I hope.
Now player 1.
Now player 1 will win. You are right. Because what will player 1 do? Player 1 will try to go to the right. 0 cannot do anything but just do this. It doesn't matter what player 1 plays here. Actually, it can do this. Let's say, and then the play will always be in this loop of 4 5 4 5 4 5 4 5 and so on. Okay. Good. So, yes. Yes. Every cycle should have a target. Is there a strategy for player 1 so that by fixing that strategy in the resulting graph, every cycle should have a target vertex? Okay. So, that is the This is the game version of the cycle detection essentially. So yeah, okay, so maybe I will, I will just do one more thing before I honestly I really do not want to be the reason between you and lunch, but I will just do this part and then we can continue in the second. Okay, so the one thing that I want to talk about is how do we translate whatever you did here into an algorithm. Okay, this is not as simple as the previous one, slightly more tricky. Okay, so how do we cleanly translate it into an algorithm? Yes.
So for this, 2 will be a winning strategy for player 1, right?
No, it can come back to 0.
See, who is controlling this? 0 is controlling, no? 0 will not do this. 0 will do it here because if this was a square vertex, then that would be winning for player 1, but this is a 0 vertex. You see, 0 has a control because 0 can just push it here. That will be 0 strategy. Yeah, good. So yeah, let me just go on to this quickly. There are there's a lot of text here. Let me just explain what it means. So okay, see, you have T. Okay, yeah, just draw it here. It's easier to use. Okay, can you all see? Yeah. See, I have my T. Okay, and then as usual, I can just compute the set of vertices from which player 1 can force the game to reach T. This is the one that we did before. Okay. So clearly, what do we know about these vertices? Player 1 cannot even reach T once. So they are clearly winning for player 0.
Yes.
Okay. But there could be more things. Why? Because previously it was enough to reach this point. Okay. But you don't know what happens here. What if this was a vertex like this from which I had this? Okay. So then those vertices are good for player 0 as well. Right. So what? Yeah, right. So what we should do is so in your first step compute this reach 1 of T, that is this part. Okay. Now in the second step look at this portion which is V minus reach 1 of T. Compute, think of this as target for player 0, because if player 0 reaches there, it is over. So compute the attractor, this is called the attractor, so call this G. Okay, compute the set of all vertices from which player 0 can force the game to go here. Okay, all this is winning for player 0. Okay, there is still a leftover part. Okay, we cannot immediately conclude what to do there, but thankfully it is a smaller game. You recursively compute. Okay, so this is a smaller game. Find the winning regions of player 0 and player 1 here. Okay, you see player 0 cannot come here because otherwise the vertex would have been here, right. So player 1 will try to keep the game in this sub game essentially, and in that sub game try to find the winning regions of player 0 and player 1 just by recursively calling the algorithm. Okay, and once you do that, this union, this entire thing is winning for player 0, whereas this is winning for player 1. Okay, it is a recursive algorithm. Let me just I will just show you the pseudocode, and it is kind of sure, wait, let me show it here. This is the pseudocode, and let me, so which part? See, up to this you got it, right. So I have a small sub game left, as in it is a smaller game, smaller graph, and 0 cannot go to this part. So like, I mean I know that 0 will be staying here roughly, right. Now in this smaller game, think of it as yet another game, okay, and just solve it. Okay, assume you call it is a recursive algorithm. So, you solve it here and you get the winning regions in this sub game. Now, I am anyway finally interested in the big game, right. What I am saying is, in the bigger game, this alone will be winning for player 1 and the rest of them will all be winning for player 0.
So you have to keep on repeating the game.
Yes, you have to keep on recursing, yeah.
So you have to check for
Player zeros where who can reach the remaining graph. Like
Yes, in
the
some
union
sense.
of the both things.
Correct. See, because already I know player 0 wins here without even reaching a vertex, T vertex.
Yeah.
Okay. Here maybe player 0 may win by visiting the vertex once, but then after that he cannot visit. You see, that will be the kind of semantics of these each regions.
So as long as there is even one path from that reachability portion which has the target, this part, this is so as long as there is even one path that allows player 0 to push it back to that
Yes.
this thing,
That will
that's
be.
a winning.
Yes, that will come into this set. The reach 0 of.
So can't we keep on doing the same thing again and again?
Uh,
I mean, check for zero players who can push into the union of the two regions we got.
Yes, essentially that is what will happen, because in the recursion, once again there is a smaller game and you will look at the vertices of T which are here and then you do the same thing. You understand what I mean? Like, see.
I mean that can't we keep on repeating the second step again and again instead of doing the recursion thing?
This
check
is,
for the
okay,
players
okay, I understand what, okay. So, I did this step once, okay.
You got that part?
What do you mean a second step? That means there is a,
Player 0 who can get into the union of the both.
but if that is the case, this thing will already be here. It's like a fixed point thing, you see. Yeah, it's like a closure of everything. Whatever is here, the edges will be like this. A very good question. Like, yeah, okay. So we cannot do this. It's not a. It's already a fixed point thing of the I iteration.
Then what else vertices we are looking for?
There could be other vertices where still player 0 cannot force to come here. You see?
And what can he do to win? Player 0?
We do not know. That is why we are asking the algorithm to figure out. You see, we cannot make a decision. So there are certain nodes where we could decide that okay, player 0 could win just by not visiting T. But in the remaining thing, there is no real reason who should win or not. So we employ the algorithm recursively.
These W's are in T, right? These W's are the target nodes.
No, W's are any set of vertices. So for instance, like in this case, W0 is 0, 1, 2. W1 is 3, 4, 5. Yes.
Is it not for the? Is it anything that does not allow player 1 to win? Is it correct to say that player 0 wins?
There is determinacy here in the sense.
So then why? So but for player 1 to win, from that situation, it should be all paths lead back to a target.
Not necessarily, because he should have an existence of a strategy.
Yes, all paths, all valid paths, all valid strategies lead back to a target vertex.
Yes, all paths that correspond to a good strategy essentially should have loops.
Yes, because that's what self-reinforcing sort of thing. You will never, the player 0 will never be able to push you out back into this thing.
Yes, yes.
So what is the way to say this? What does it mean, good
Ah,
strategy?
okay. So, see, first of all, a strategy is just a function like this, right?
Yes, it's transition function.
Just, okay. So, once I give you a strategy, for every player 1 vertex, you just keep that strategy edge. Just delete everything else.
Okay, but I'm saying then why can't I apply that property to test for winning strategies for player 1?
So, yes, that will give you an NP procedure, because you will guess the strategy, right?
So I see why this problem was open. This was open for a very long time, like having a
Yes.
not being able to.
See, the Bushi case is easy, okay, we will do it early, but I will come to the parity case where the guessing is, so far we do not know what else to do, like, I mean, so here we can, this recursion, see, this is an algorithm which is like ONM, okay, because you recurse at most n times, because each time you have a smaller thing and each computation does m work. So, this gives O n m.
Do we stop if the size is 1? If the size of W naught or W1 is 1?
Good question. You are right. Very good question. So, this is the stopping criterion, which is, suppose this part was empty, okay, then there is no way for player 0 to get out to anything good, okay. And of course, one has to show that you will reach such a situation and so on, right.
Sir, could we have this sort of way of finding, like we did in the previous reachability question, we find all the nodes that from where one can force the game to go to
Yes.
the target vertices, and then any loop among those vertices that contains a target vertex will be the winning thing, and no, nothing else.
No. I will try to generate an example where that doesn't work, okay. So, it will take some time, but it is not. So, you are saying that I first take all vertices from, all vertices where one can force the game to go to a target vertex, yes, and then you are saying I take inside this, I look at all vertices that are part of a loop containing this. It should not work, okay. I will tell you why. Because there could be like some other inside that loop, player 0 could have some way to get out. Maybe it is not that. Wait. I understand. Okay.
That guy would have been considered already to be going back.
Okay, you are saying that.
If there was any edge to go back.
You are saying that. Okay. My gut feeling is that it should not be should not be like that. But let me try to work out. It's a very good proposal. Very nice proposal. Let's try to think about it.
The circular node could go back.
That's what she's saying. Like
Another option. Another option.
Because
not a
all
part of
circular nodes in our loop have, for all paths they are going to T. That is what our subset was, right, when we were doing the reachability.
So you're saying that, okay. So you are left with a graph in which in every loop in every loop there is a target vertex.
Yeah, and every other vertex has either it's a square vertex with one edge to T or a circular vertex with all edge to T.
So how do you find that?
That is what we did in the first part, right?
No. So in order to find that, you will probably end up doing this work, I think. So you are describing the set of vertices which are winning essentially. Okay. So there is always this there exists for all kind of thing, which is very different from cycle detection. Finally, we will end up in such a thing. The goal is to find that.
And yeah, even if there is, it's not detecting one cycle, you're trying to detect a very specific kind of a cycle.
Yeah.
Then in that case, any small possible cycle itself could be exponential.
Yes. No, we don't want to.
So we want a very specific, this sort of cyclic things, we want a very specific type of cycle.
It's more
like
like
this sort of a loop thing. Why can't we think of like for player 1 to win, he has to get into some kind of a cycle situation where he keeps on moving around target.
Yes, no matter. See, the thing is, player 1 cannot force the game to go into one cycle.
Unless
because player 0 can do other things.
Right, so there cannot be a back edge that allows player 0 to push this.
Yeah, roughly that's so. Yeah.
So if you could detect those edges, like all edges that allow. Okay, I say of course this is characterize what exactly it is we are looking for.
Yes. Essentially, exists a strategy such that for all cycles in this restricted graph, there is a target vertex.
That is
necessary and sufficient.
And all of them should be like that.
Yes, because otherwise 0 will force the game.
All the 0 places that are there, its neighborhood lies in that loop only. So then that would say that this loop is better for us because it can't exit the loop. All its neighborhood are in that loop. So then this loop is what we are searching for.
Kind of. It's not just neighborhood, it's a winning set in some sense.
Like whatever zeros that we have in the loop, those neighborhoods are in the loop itself. So it can't escape the loop.
Yes, more or less. That's what we are looking for. It's just, I would not say loop, I would just say set. That's all. Okay.
Because in this infinite, we need a loop to continue.
Correct. Guys, I think it's a good time to stop. I think all of us have worked hard for the, and so I think it's a
So
good.
this is a good place to stop so that we can start.
Yeah, well, I mean, I had more things for lecture 1, but maybe.
But it's okay, we can go at 1, 5, 10. I took too much time.
No. No, because.
Please, I miss CY lunch.
No, I'll tell you why. Because the next is parity games.
It'll take time.
It will take time to explain and so on. So I will.
That's
It's a good point to stop actually.